Greetings, welcome back. Session 7, Part 2, Decision Tree. In the previous recording, we spoke of the concept of decision tree and why we do it. It is a very simple approach. Anybody can do it. You don't really need to have domain knowledge. Someone is going to actually create the table, a database, that is usually a structured data. And the person who is doing structured data for you is the one who has the domain knowledge, for example. And then your task as a data scientist is to see whether you can basically make decision at every branch of the tree. We spoke of the tree. Let's get back to the last concept we spoke of. We had as considered bags of cookies. You have bags of cookies that are identical. Definitely you are going to say, I like them or I don't like them. Therefore, the decision is very easy to do. And if that is the case, the entropy, because the probability when you put your hand inside the jar to pick up a cookie is going to be exactly, yes, I like them, exactly, no, I don't like them. So if all of them are yes and all of them are no, when you put your hand inside and you pick up a cookie, you know what the decision is. For that, the probability will be 1. And therefore, as we take the log of 2 of 1, it's going to be 0, and the outcome is going to be 0. So the entropy will be 0 for the case where the bags are pure, exactly reflecting your taste, all of them. Now, if you have a bag that is going to be 50 of the cookies that you like, and 50 of the cookies that you don't like, when you put your hand inside the jar to pick up the cookie, you really don't know whether you are going to like it or not if you haven't picked them up randomly. And in that case, we are going to say the probability is going to be 50-50. So it's 50%, which is 0.5. 0.5 means 1 over 2. Log of 2 of 1 over 2 is going to be minus 1. Minus 1 and minus half. Minus 1 and minus half. Together, it's going to return to you 1. For the maximum entropy of 1, it means decision is very difficult to make. It's not pure. It's actually impure. That's what we say. With that in mind, this is the approach we have. We want to go in and study the entropy in different ways and then come up with the decision at the end. I'm going to explain a few examples from the sites, and then I'm going to take you to my slide, and I'm going to show you more examples there. So let's take a look at this one. What is a decision tree? Imagine you have a structured data. This is going to be an Excel file or Excel sheet. You have predictors, attributes, outlook, temperature, humidity, windy weather or not, and the target is going to go whether you are going to play golf or tennis. This is actually a very common, very popular example that you could potentially find in many textbooks as well as internet. Now, if you take a look at this, this is in form of a table. It doesn't necessarily help you to make a decision by looking at the Excel sheet. We are going to translate that into basically a decision tree. Different people have actually plotted decision tree in different forms. This is one of the forms that I couldn't modify, so I'm going to stick to it for now. Then you're going to see a different type of a slightly changed schematics for the decision tree in my slides. So I'm going to take a look at the outlook, and outlook could potentially be, if you take a look at it, sunny, overcast, and rainy. Sunny, overcast, and rainy. Now, if you take a look at overcast, you're going to see overcast is yes, overcast is yes, overcast is yes, and overcast is yes. So if there is overcast prediction, then you are going to play golf, right? So that's what this one is. So keep this in mind that overcast has a pure set at the end. The decision is simple. If it is overcast, go for it. So that's why overcast is going to give you the terminating point, which is decision is yes. Now, if it is sunny, though, if you take a look at sunny and windy, false. It's not happening. It's not windy. Sunny, windy, false. You got yes, yes. And then sunny, true, windy, you got no. Then you have sunny and false, you got yes. You have sunny and true, you got no. This is not pure anymore. You can see some yeses and you can see some no's. And it depends on whether the windy situation condition is true and the windy condition is false. So we basically need to actually analyze that. You could potentially go into the rainy mode and then take a look at the humidity and relate to that. So you have basically the rainy and the humidity, high and normal, and we have only two basically cases. So high and normal, and then what happens is that you could potentially count the number of yeses and the number of no's. What happened? We basically translated an Excel file into a tree. Now, let's take a look at this. This, we said that this is going to be the entropy for a single attribute. That single attribute could be anything. So you do have a number of attributes here. If you say that the single attribute is going to be play golf, yes or no, that would be the end. That column becomes your focus point. If you say, I'm going to take a look at the, for example, outlook and humidity, outlook and windy, then you have two attributes you're going to take care of. If you have one attribute, which is, for example, in this case, for the sake of our own simple approach, let's say play golf is the attribute I'm going to do, and you have yeses and nos. Let's see what we have to do. If you count the number of yeses, so take a look at the yes. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 yeses. Take a look at no. Of course, we know if it is 14 rows, then no has to be 5. 14 minus 9 is going to be 5. 1 and 2, and then 3, and then 4, and then 5. So what do we have? It's a simple table now. We don't have complex table now. This is a small, extremely small, but keep in mind, as a data scientist, you are dealing with thousands and millions of rows and potentially tens of hundreds or thousands of columns. So we are trying to give this as a simple example so that we understand what is happening. Now, we have 9 yeses and we have 5 no's, and the single attribute is going to be play golf. The way we are going to do, we are going to calculate the entropy. 5 over 14, 5 plus 9 is 14. 5 over 14, you get 0.36. 9 over 14, you get 0.64. So we want to calculate the entropy of this. So the way it's going to work is this: 0.36, that's the probability, times log of 2, 0.36, 0.64, log of 2, 0.64. You do the calculation, you do the math, you consider this minus sign at the end of the day, and you get 0.94. What does that mean? 0.94 means it is relatively close to 1. It means that your set is not pure, definitely, and it is not an easy way to make a decision on. So you can't just say they are necessarily equal, or they are, I'm sorry, you cannot say that all of them are yes or all of them are no. By looking at it, you will not be able to make a decision. That's the impurity of this table. Now, if you go back to the table, and if you happen to have 2 attributes at the same time, the way we are going to do it, we are going to actually calculate, or 3 or multiple attributes at the same time. We are going to do the probability times the entropy of the value we are looking at. So in this case, I'm going to say play golf and outlook. Play golf and outlook. So I have 2 attributes. One of them is the target. One of them is the basically incoming input. Input is independent, outlook. Play golf is going to be dependent, hopefully based on the outlook. We talk about independent and dependent variables when we get to Bayesian techniques in a moment. Now, we have P of sunny. So let's take a look at this table before I actually calculate this for you. So I do have the outlook. The outlook is sunny, overcast, and rainy. Play golf. Now I have the 2 attributes on basically vertical position together. I count the number of yes, play golf for sunny, no, play golf for sunny. yes, play golf for overcast, 0, play golf for overcast, actually 0, no play golf for overcast, 2, yes for play golf rainy, 3, no for play golf rainy. So where did we get it? We got it from this table. So you have overcast, overcast we spoke of it last time, rainy you get 1 and 2 no, and then another rainy, this is no 3, and then this is 1 yes, and this is 1 yes 2, and that's it. So 2 and 3. So that's how we got this table. This table is an easy count process. You could do that in Python. You could do that by hand on a piece of a paper. So I would have, how many sunnies do I have? I have the sunny cases, I have 5 of them. Obviously, that's a simple addition of 3 and 2. Overcast 4 and 0, 4. Rainy 2 and 3 is going to be 5. And obviously, if you add them up, you're going to get 14. Okay, so let's take a look at this and see what happens. The probability of sunny. What is the probability of sunny? The probability of sunny is 5 over 14. The probability of overcast is 4 over 14. The probability of rainy is 5 over 14. So I do have these fractions behind the E of the calculation that we are going to do in a moment. Then we have the entropy of 3 and 2. Remember the way we calculated that. 3 and 2, we are going to say 3 divided by 5 and 2 divided by 5. So 3 and 2 is 5. So it's going to be 3 divided by 5, 2 over 5. 4 divided by 4, 0 over 4. 2 divided by 5, 3 divided by 5. So we are going to calculate the entropy, and when we calculate them, we get 0.693. What does that mean? It means that if you consider outlook, considering the dependent variable play golf, where the yes and no's would be important to you, you basically are closer to basically making a decision. Take a look at this. 3 and 4 is going to be considering the outlook. So if you take a look at this, you will see that all the time, almost, not all the time, most of the time, 3 is bigger than 2, 4 is bigger than 0, and 2 is not far off from 3. Kind of 50-50. So if I wanted to say, can I make a decision on this? Yeah, I would, possibly. That's the way you are going. I think so, right? So 0.693 reflects the way you see this data. Now we go into, so basically we have already calculated the single attribute. We got to the 0.94, and then we had, then we have something else. What we call is the gain, information gain. Now take a look at this. This is 0.693 if we considered outlook as our branching component. So let's take a look at this. If we consider outlook at the top, what happened? You might say, who told you to accept outlook as your primary divisions? Who told you to put outlook first and then go windy and humidity underneath and all of those? Yes. Are we going to put outlook first? Are we going to put windy first? Are we going to put humidity first? Which one is going to give you the maximum information gain? So let me explain what the information gain is in a moment. So the way we did it is that for the yes and no of a single entropy, we got 0.94, and then for the outlook as the primary divisive component, we got 0.693. We simply subtract that. So when we subtract that, we get 0.247. Now you have the right to ask this question. So this is the gain. This is the gain if we have the outlook as the primary attribute at the very top, and then branch them out, right? Do you remember what the decision tree was? This is the first, the root node, then you have the secondary layers, then the third layers, and you make the decision down. Which one is going to help you to make the decision faster? So that would be the question. What would be the optimum approach from the root node to the leaf node, to the terminal point at where you could potentially make a decision? So that's what we are trying to do. In the decision tree, we are going to ask ourselves, is it better to have outlook as the primary divisive component? Is it better to have temperature? Is it better to have windy? Is it better to have humidity? If you take a look at this screen, you can see that I have actually calculated the gain, information gain. How did I do that? For a single play golf attribute, I've got 0.94 something. Then when I combine it with one of these attributes, I'm going to find the basically entropy, and then I'm going to subtract these two entropies. So I'm going to subtract 0.247, 0.029, 0.048, 0.152. Then I'm going to pick up the maximum, because when I get the because if you take a look at my table, the reason I would like to have the maximum gain is that, remember, if the maximum gain was 1, right, what would have happened? You have 1 initially, just a kind of a consideration. If you had your single component 1, which was 50-50, remember that? And then you have maximum gain of 1. What happens? 1 minus 1, what does it give you? 0. What is 0 representing to you? 0 means you have a clear-cut decision to make. So the reason we're looking for maximum gain is because we want this to be as moving towards 0. So you do have 0.94. When you subtracted the entropy of this table, you got 0.24. Would you like, which one would you prefer to choose? Which one of these information gain is going to get you closer to 0 that you want? So obviously, I'm going to get this one, because these are not going to move me tremendously. This is not going to move me tremendously. This may, but not as much as this one. It is going to take you down to 0. That's the information gain. So that's why we are looking for maximum information gain. And when we find the maximum information gain, we are going to put outlook as the primary attribute at the top, and then look at everything else underneath. I wanted to take you on this trip so that you know what we are trying to do. And remember, this is going to be eventually what we call a branching technique. Branch and bound, sometimes they say, branching technique. So if you take a look at outlook, I'm going to have rainy, I'm going to have overcast, I'm going to have sunny. Now the outlook is here. You could potentially tag it with one of these. Remember, in the original decision tree, you were looking at play golf. Now the next stage, you're actually going to relate outlook and windy, outlook and humidity, and so on. So that's what we are going to do. We are actually going one stage further, and we're going to see the relationship. And then as you go in, you're going to make decisions. For example, this one, overcast, as we have discussed, is a clear-cut decision. And then you're going to have windy, and you're going to calculate, and you are going to move ahead, and so on. I wanted to go through this process because it has a very nice Excel sheet, small tables that would be easy for us to calculate. I'm going to take you to my slide with the similar stuff, but I'm going to talk about the decision tree in more detail. Thank you very much. Stay tuned.